All right, today we're going to look at topic 4.6 on titration. We have already covered unit 4, so we're just picking up this topic that we skipped at the time due to timing. So we will use titration to determine the concentration of an analyte based on the equivalence point. So titration is a lab technique. We've looked at multiple lab techniques this year, like chromatography, distillation, filtration. So we're adding this to our list of lab techniques, and its purpose is to determine the concentration of a chemical. So titration, it is used, like I said, to determine the concentration of a chemical through a chemical reaction. So we're trying to determine the molarity of a chemical, or its concentration, by reacting it with another chemical. So this reaction is a good example of one that might be done using titration. So we have HCl, hydrochloric acid, which is aqueous, and sodium hydroxide, NaOH, that's aqueous. When they react, they form water and sodium chloride, which would also be aqueous and stay dissolved. So basically, we're making salt water. Now, if we know the concentration of the NaOH, we can react it with an unknown concentration of HCl to find out HCl's concentration. The only catch is that we would need to know when the exact stoichiometric amount of NaOH has been added to react with all of the HCl and have no excess. So our goal here is, if we know we're reacting, say, 0.5 moles of NaOH, we have to also, to have that perfect amount, we would want an equal quantity of HCl based on the balanced reaction. We can see the coefficients are 1 to 1, so we would need equal amounts or equal moles of each chemical. So we need to know when to stop our reaction, when to quit adding NaOH, and that's done through titration. So let's take a look at the equipment and setup of a titration. So the equipment we have here, let's start listing it. On the left, we have a ring stand and a clamp of some sort, sometimes a burette clamp, sometimes just a regular utility clamp. On the right side, we have a burette. It has a little valve here to open and close that burette and allow liquid to drain. And then down here we have a flask, and we have some chemicals involved here. So in the burette, we're going to add what's called the standard solution, and that's one that we know the molarity of. So we have the molarity of that solution. Also, because it's a burette, we can measure its initial volume. We can fill it to the 0 milliliter mark, or a little bit lower than that. Maybe it starts at 1 milliliter or something. As long as we record that, we have an initial volume. And then we would end up later during the experiment draining liquid and ending at some lower volume. So we will also have the volume of our chemical in liters. So with molarity and volume of that chemical, we can find moles, which is a great thing to be able to find. As we've seen, so many things relate to moles. So if we can find the moles of a chemical, we can do lots of calculations with that and find out missing information. Speaking of missing information, down here in the flask, that is where our unknown solution, or the analyte, is placed. So the chemical we don't know the molarity of. So we have a question there. No, we don't have a value for the molarity, but we would know the volume, right? We could check that off our list. We'd have the volume of that solution. So if we wanted to find the molarity, and that's the whole point of titration, is to find the concentration of your analyte, then we would need to find molarity. Its equation is moles per liter. If we have the volume, we would need the moles. So we're going to do a chemical reaction to lead us from the moles of one chemical to the moles of another chemical. And therefore, we can find the molarity. So the way this is set up is we would have our burette with our standard solution, our flask with our analyte typically, and we would start opening that valve and adding the standard solution to the analyte. And we do that until it says the equivalence point is reached. And we'll talk about on the next slide what that equivalence point is and what it looks like. Then we do our calculations because we'd be able to read our final volume and find moles of our standard solution. We could then do our calculations to find that molarity of the unknown. So let's talk about the equivalence point and also the end point, how they're similar and or different from each other. So using that chemical reaction we have as our example, the equivalence point is when equivalent moles of reactants have been added according to the balanced reaction so that all the reactants are used with no excess. So in this case, the HCl and NaOH, the reactants, are a 1-to-1 ratio. So that means we would want to react that ratio with each other. So say we had 0.75 moles of HCl, we'd need 0.75 moles of NaOH. We need equivalent amounts based on that balanced reaction. So that is our goal. The equivalence point is when we have equivalent moles based on our balanced reaction. Now, how do we find the equivalence point? HCl is a clear liquid when it's aqueous. NaOH is a clear liquid when it's aqueous. When we add them together, we're making salt water, which is a clear liquid, and it being aqueous. So we have to have some way of knowing when we've gotten the exact amount we want. And there's different measurements that we can use. We can use conductivity because we're going to have a certain amount of conductivity in our reactants and our products. We could graph that and determine our equivalence point. We can also use pH, which is a very common one since many of these reactions are done with acids and bases, and pH is a way to measure the strength of your acids and bases, strength and concentration. The other thing we can use is estimating our equivalence point and getting really close to it using a color change by an indicator. So when the color change indicates the desired pH, we call it the end point. So when we get that color change that we want, we call that the end point, and it is an estimate of the equivalence point. So they're related, but they're not always exactly the same. So when we're looking for a specific color, we call that the end point. Let's take a look at what an indicator is. So we have this pH indicator chart, and we'll take a look at that more in depth. But an indicator is a special chemical that when exposed to different pH levels will change color. So it's a way of measuring pH without actually having to measure the values of pH. So they are often used in titration because the color change can indicate where the equivalence point has, or when the equivalence point has been reached. The indicator is chosen based on the chemicals that are reacting. So for the reaction given on the previous slide, we had HCl plus NaOH, and it made salt and water. So our products of this reaction, it starts out, if we're looking at our flask at the bottom, let's say our flask at the bottom had the hydrochloric acid. So it would start with a low pH. And as we add the NaOH into that flask from the burette, our pH is going to go up. Okay, we're going to increase that pH. Acids have low pH, bases have a high pH. Well, it should have a final pH because it's making salt and water. So as we use up the HCl and the NaOH, we are going to make salt water. So it should have a final pH near 7 because all of our HCl and NaOH has been converted to sodium chloride and water. So when we've used up all of our reactants, then we'll have salt water, and it should have a pH around 7. So we typically use phenolphthalein for this reaction. We can see when it's acidic, it stays nice and clear. And then as we approach that pH 7, we start to get this, and above that, we get this magenta pink on the right side where we get this high pH. So right at 7, we're actually going to get a pH that is close to, so at pH 7, it's going to have a very, very faint light pink color that will last a little bit of time and may fade to clear. So that's what we look for when we're doing this titration. We're going to look for having a nice clear solution, and as we start to add more of the NaOH, we're going to see these dark magenta drops fall in, and then it will turn clear. And when we get this light pink, I like to call it baby girl pink, that's when we would stop our titration, and we would know that we've reached the end point of our reaction where the color change has occurred, and we will estimate our equivalence point based off of that information. So let's take a look at a visual of what's going on here. So we can see that in this case, the base is in our burette. So that would be like our sodium hydroxide dripping from our burette. And then our HCl would be in our flask. And you can see they're adding a drop at a time of the base. And you're starting to get that faint pink color, faint magenta. Now, if you add too much base into it, it turns this dark magenta. So that's how you know you've gone too far. So you've gone past your equivalence point and you would have to start over. Typically we run a reaction really fast the first time so we can see about how much volume it takes to titrate it, and then we go back and do a slower one to get better data. So this is what it would look like, and you can see they're swirling it to make sure it mixes really well. We would also rinse off the tip of the burette and the sides of the flask with distilled water to make sure that all of it's rinsed into the flask and all the chemicals are reacting with each other. Here is the general process for a titration. So first, the solution of unknown concentration, our analyte, is measured into the Erlenmeyer flask, and the volume of that is recorded. We measure it very carefully. A few drops of indicator are added to the flask, and then the burette is filled with our standard or known solution. We would record its initial volume. Then, while swirling the flask, the standard solution from the burette is added to the unknown. First, we do it quickly. Then as the change starts to last longer, we switch to smaller drops and wait until the color change lasts about 20 seconds. So we get that light pink for about 20 seconds at least. And we stop when this occurs. We'd record the volume of that standard solution on our burette. So we have its initial and final volume, and we could find out how much was added from the burette. To do the calculations, we will use a set of sample data and work through that. So a student titrates 15 milliliters of HCl. So when they say they titrate it, that means that that's the chemical in the flask, and we say it's being titrated, meaning another chemical is being added to it. So the HCl is in our flask in this case, and a standard NaOH solution is in our burette. So I like to draw a little picture of where the chemicals are and what I know about them. So we know we have 15 milliliters of HCl, and I know my molarity of the standard solution. So that's the information we start with before we've done any reactions. And then the data below was collected. We want to find the concentration or molarity of the HCl. So it gives us, we have our molarity of our standard solution. We already knew that. We have an initial and a final volume of the standard solution. So what we always want to do, making sure that we're looking at the same chemicals, so standard solution is our NaOH. We want to subtract those two values to find the change in volume, how much we actually used. Well, it started at 0, and we've drained from the burette 12.54 milliliters. So that means that we used 12.54 milliliters of our standard solution. So using that information, we also have our volume of our unknown that was already given. So really the only two things we're recording during the reaction are our initial and final volumes of our standard solution. So we want to find that unknown molarity. There's a couple ways we can do this. And I'm going to show you first what's listed here. It says we use the molarity equation and mole ratios to find the concentration of the unknown. So for the NaOH, right now I have the most information about it. I have a molarity and a volume in milliliters. If I do molarity times liters, I can get my moles of that chemical. So we've got 1.50 times, if we convert these 12.54 milliliters into liters, we move that decimal 3 places and basically dividing by 1,000. So we get 0.01254, keeping all your significant figures. So we've got molarity times liters, and that's going to give us our moles. So let's go ahead and do that calculation. Pulling up my calculator. 1.5 times 0.01254, and I get 0.018, and we've got 3 sig figs there, so 188 moles. And that's of our NaOH. Okay. It says, so we're using that molarity equation, and a mole ratio. The job of our mole ratio is to change chemicals. This is a really important step here. So we don't want NaOH, we want to know the molarity of HCl, of that unknown. So we have to do a mole ratio. Well, we can look at our balanced reaction, and in this case, it's a 1-to-1 ratio. So 1-to-1 ratio. In that case, you don't have to show your calculation for your mole ratio. You can go ahead and just rewrite this as 0.0188 moles of HCl. We know that because it's a 1-to-1 ratio. So now we can find the molarity of our HCl. So this part's about HCl now. Okay, so we did our NaOH part, which we knew. Now we're doing our unknown HCl. To find its molarity, we want moles per liter. We have our moles. We've calculated those. 0.188 moles. And our volume, we have had our volume since the beginning. 15 milliliters is going to be 0.01500 liters, keeping all of our significant figures. So 0.0188 divided by 0.01500, and we get 1.25, we've got 3 significant figures, molar HCl. Right? So if we react 15 milliliters of HCl with 12.54 milliliters of 1.5 molar NaOH, we can find that the concentration or molarity of HCl is 1.25 molar. So it's using equations and things we've already done. The math is not new here. Nothing is new here. All of this math was learned in Honors Chem. The only thing we're doing is putting it together with the lab situation to find a value we didn't know. So let's do the calculations for another set of data. It says, given the following data, calculate the molarity of the acid using the data below. Calcium hydroxide is 1.75 molar. So we've got some information about our chemicals. We've got the volume of HCl added to the flask. So we've got our little flask at the bottom. We know that that's HCl and that it has 30 milliliters in it. We're adding to it calcium hydroxide. And we know its molarity is 1.75. And then we have some data here. So it says our initial and final volumes of calcium hydroxide in the burette. Now, so it's initially at 0.5 and it ends at 43.2. So we need to first find the change in volume there. We need to subtract them. So 43.20 minus 0.50. And we're going to get 42.70 milliliters, keeping that 0 because it is significant. So we know we're using 42.70 milliliters of our calcium hydroxide. That's a pretty significant amount because our burette only holds 50 milliliters. So that's using most of that volume. So again, we're going to start with the one that we know the molarity and volume of. So we're going to start with calcium hydroxide. So again, molarity times liters gives us moles. Our molarity is 1.75. Our volume in liters, move that decimal 3 places. So 0.04270 liters, and that's going to give us our moles. So let's go ahead and calculate that. 1.75 times 0.0427 gives us 0.074, and we have 3 significant figures, so 747 moles of calcium hydroxide. Oops, my 2 goes on the outside of the parentheses there. Okay. Now, looking at my balanced reaction, I need to change from calcium hydroxide. I need to get to HCl because that's what I'm looking for, right? So now I'm going over that gap between our 2 chemicals here. So that means we have to use the mole ratio. Now, it's not 1-to-1. I can't just copy that number. So let's go ahead and do the mole ratio. We've got moles of calcium hydroxide, and we're going to moles of HCl. And we're going to look at our coefficients on our balanced reaction. So 1 mole of calcium hydroxide is 2 moles of HCl. So now we're going to be at HCl. I'm going to go ahead and change my color here so we can keep track. So we have 0.0747 times 2 gives us 0.1494, so 149 moles of HCl. Remember, our goal here is to find the concentration, the molarity of HCl. Molarity is moles divided by liters. So we need to take those moles of HCl, we're going to divide it by the volume of HCl, which we have. In milliliters, we're going to move that decimal 3 places. So 0.0300 liters of HCl. So 0.149 divided by 0.03000, and we get 4.96, and the 6's do continue, so we want to round that up. Again, we have 3 significant figures, so 4.97 molar HCl. So let's take a look and kind of analyze this. That means this HCl is 4.97 molar. So we have a pretty significant amount, 30 milliliters, of a pretty high molarity solution, 4.97, almost 5 molar. So that's why when we have a low molarity on the calcium hydroxide, 1.75, it took a lot of it, 42 milliliters, to react, right? To get that equivalence point, to find that proper 1-to-2 mole ratio between the two, where we had 1 mole of calcium hydroxide for every 2 moles of HCl, having that ratio. So this is how we can do the calculations. We can use our molarity equation basically twice with a mole ratio in the middle. So we use our molarity equation to find moles, do our mole ratio, and then use our moles to find our molarity of our other chemical. Now there is an alternative way to do this. I'm going to also show you that, and you can choose which way makes the most sense to you and is the easiest for you to process. Both of them are completely valid as long as you follow all the steps. So let's take a look at that. Okay, I'm going to show you a secondary method now of how to do this calculation, and I've written an equation at the top. You'll see if you ignore the part that says number of hydrogen, number of OH, it's molarity times volume equals molarity times volume. So it's essentially our dilution equation, M1V1 equals M2V2, but instead of 1 and 2, we've replaced it with A and B for acid and base, and it incorporates the mole ratio for us using this extended equation with our hydrogens and hydroxides. So it really cuts all of the calculations on the previous slide into one equation. So that's kind of how why I like this one, but it does require you to kind of memorize this equation because this is not something that's given on your equation sheet. Your basic molarity equation is. So it just depends on what you're more comfortable with. So let's take the same situation as our last slide. We've got that 1.75 molar calcium hydroxide. We know our volume of our HCl that's added. When we subtract these two, we got 42.70 milliliters of base added. So let's plug this all into our equation here, and I'll show you how to get these two numbers in front and calculate. Remember, our goal is to find our molarity of HCl, which is our acid. So we're trying to find that value there. So I'm going to go ahead and plug everything in without rearranging anything. So the first thing, we're looking for our molarity of our acid. I'm going to leave that. So the little A there is just a label. And that's going to be multiplied by our volume of our acid. In this case, HCl is 30 milliliters. The other nice thing about this is you can leave your stuff in milliliters. We'll come back to that number of hydrogen. And we'll come back to the number of hydroxide. So our molarity of our base is given at the top, 1.75 molar times its volume. When we subtract them, we get 42.70 milliliters. So we've got that. Now, these number of hydrogen, number of hydroxide, that comes from our balance equation. So our number of hydrogen that are reacting. So our hydrogen comes from our acid. So we have two of those reacting, two HCl's are reacting for every one calcium hydroxide. So I am reacting, oh, sorry, excuse me. Let me go back for a second here. It's not using the coefficients here, where we are reacting two HCl's for every one calcium hydroxide, but what we want is the number of hydrogens in our acid. My bad. So we have one hydrogen in our acid there. On the other side, how many hydroxides are in our base? We have two hydroxides in our base. So just in the chemical formula, okay? So let's take a look and go ahead and do our calculation here. So we've got on the left 1 times 30 milliliters times our molarity of our acid. So we have just molarity of acid times 30 milliliters. So we'll simplify that. On the right side, we have a little calculation to do. So we have 2 times 1.75 times 42.70. And we get 149.45. And this is kind of just a stopping point. I'm not going to round yet. Now we have our molarity times our milliliters. I'm not going to worry about canceling any units yet until the end. So now we want to rearrange and get our MA by itself, our molarity of our acid. So we're going to do that by dividing both sides by our 30 milliliters. And our milliliters are going to cancel. We're going to be left with molarity here. So our molarity of our acid, our HCl, is going to be 149.45 divided by 30. And we get 4.98. And just keep going. Now, in terms of significant figures, you can refer back to all of your values. We've got 4 there, 3 there, and 4 there. So let's go ahead and round it to 3 sig figs, and that would be our molarity of our HCl. So that is essentially the same as what we calculated on the previous slide, but in a faster way. So just to clarify, our number of hydrogens comes from our formula. So in HCl, there's 1 hydrogen. Our number of hydroxides comes from our formula, CaOH, 2. There's 2 hydroxides. So that's where we got the 1 and the 2. So it incorporates that mole ratio, but in a different way. And I think it's a little more straightforward this way. If you wanted to go ahead and set it up and rearrange everything and then solve all in one calculation, you can do that too. But we do get the same answer. So whichever way you're more comfortable with, I would stick to. Just practice one way and use it and know it. So this information will allow you to go ahead and do some practice on the titration calculations. More about the lab technique with pointers, setup, information, all that we're going to look at in our pre-lab for our first titration experiment. We get back to class. So practice those calculations, determine which method you want to use, and get comfortable with it. Thanks, guys.